Hey guys, here's a video for 13.1. I'm just going to show you a quick demo as long as I have my classroom for a day. I put a pencil in this spring to keep it, trying to hold it a little bit, but way back in chapter, I don't know, Dynamics, the Dynamics unit, we had something like this. We had a springs. We attached something to like this is a frictionless surface, some mass on a frictionless surface, and we let go, and it goes back and forth, and of course in real life there's friction. But we're going to pretend like this just oscillates back and forth forever with a periodic motion. Anything that repeats is a periodic motion. And we talked about period back when we had like a planet going around the sun. Period is how long it takes to complete one cycle. So that'll show up again. But we're going to start here with this kind of simple setup, and then we'll develop farther and more complex things from there. But this is the start of 13.1, and then I'm going to show you here some pictures, and we'll do some looking at it on a piece of paper. So let's just start with this, just a mass attached to a spring, and the spring is at its relaxed length. The mass doesn't get pushed to the left, it doesn't get pushed to the right. But if we displace that mass, say to the left, we squish the spring will apply a force to the right. And if we pull the mass to the right and stretch the spring will pull the mass to the left. And so we had an equation Fs equals Kx called Hooke's law. If you want to see it, and I showed you this before, but it's been a while. The equation looks like this. The spring force equals K times delta X. I'm still going to use the delta. The book uses just X. When the book uses X, X0 has to be, or X equals 0, has to be the equilibrium position of the spring. So that anything over here is negative, anything over here is positive. So you'll see that if we displace the mass to the left, the force is to the right. If we displace the mass to the right, the force is to the left. So instead of getting the spring force equals K delta X, there's a minus sign to switch the direction of the force. All right? And then imagine we have some situation where we take the mass and we could stretch it. I squished it. Squished the spring. Some distance A. And then we're going to let go. If we let go, this mass is going to come back through here and go to the right, slow down and stop, come back and oscillate back and forth, back and forth, back and forth. So let's use energy, I guess. Let's see what happens if this object starts at rest. The only energy, so the E naught would be 1/2 K delta X squared for the initial squish. And then let's figure out how far does it go to the right. Well, at the end, when it goes to the right and stops, how far over is that? So E naught plus work external, there's no work external, there's no friction, so this is plus 0 if you want, equals E final, which is 1/2 K delta X at the end squared. And it stops, so we're just picking some spot. Where does it spot when it comes over? Where does it stop? When it comes over here. And if you notice, you can cancel out the 1/2, you can cancel out the K, and it turns out that their distances, not their directions, of course, but their distances will be the same. So it will go over here to the same distance A, and the A we call the amplitude. And you've probably seen things like this in your math class. So it's going to oscillate back and forth, and this will be the equilibrium position. That was this original spot where the spring was neither stretched or squished. Okay, so it's going to oscillate back and forth, and the only force on this object is going to be that spring force. So that will be our mass times our acceleration. The book decides to solve for the acceleration. I don't like to memorize formulas. I like to memorize things, or start with basic concepts. We're starting with Newton's second law, so really I'm doing F net equals ma. Sorry, get my hand out of there. And so F net equals ma, Fs equals minus K delta X is ma. So A, they say, is minus K delta X over m. But I wouldn't worry too much about that equation. Okay, so that's where we're going to start. And if we were to graph this guy's position as go back and forth and back and forth and back and forth, wish we could I would do some other demos and stuff if it was a little easier in class, if you were here. But we're going to make a graph of position versus time, and realize the position, as this goes this way, this is going this way. Okay, back and forth, back and forth, back and forth. And actually for this one, let's start out here and let go. Let's pull the mass out so that it's at A, and then let go. What's going to happen is it's going to go back towards 0. It's going to start up here at A and then go back towards 0. And then it's going to go to negative A, down here somewhere. And then it's going to go back to 0, and then back to A, and then repeat again. Repeat, repeat, repeat. So what should the shape of the graph look like? And you probably already have a guess, but as delta x gets big when it's, say, way out here, or say when it's it's a negative delta x, but when the magnitude, the squish or stretch is big, the acceleration is big. When the magnitude of delta x is big, the acceleration's magnitude will be big, but the velocity is very small. We said this is where it started at rest, and that was where it ends at rest. So if the velocity is small, that means we know the slope there is 0, and when it gets way over here to negative a, that slope should be 0. When it's there, it's going to the left, its slope should be negative, and when it gets back to here, that spot, the slope should be positive. And you will see, and you probably believe me, we can do a derivation of this, but I'll try to get my hand out of the way as I draw these things. It ends up making in this case, if we start out here, it ends up making a cosine graph, and it will repeat. The time it takes to complete one cycle, to go from some spot back to that same spot again, it could be from over here, starting there, to go there and back. We could start here and go back. We could go middle going to the right to middle going to the right again. It doesn't matter. That's called a period. So the period would be this time there, would be the time from where you started to where you get back to that same spot. And so we've seen this before. It's a capital T is the period. And then there's another thing we haven't talked quite so much about, but let's suppose that it does, it goes back and forth here in a quarter, sorry, it goes back and forth here. This is 1/4 of a second. Suppose that the period is 1/4 of a second. Well, how many cycles does it complete in 1 second? If it takes 1/4 of a second to complete one cycle, in one cycle it can complete 4 cycles in 1 second. So that's called the frequency, which is the cycles per second. Whatever it is we're talking about. And I like to say to my students, this could be, how often do you eat ice cream? You might say once per week, or twice a day, or 3 times a month. You'd give me some number per time. That's how frequently you eat ice cream. So a frequency, just think of it as how often. In this case, it's how often it completes a cycle, how many times, and we could use different units than seconds, but we tend to use seconds. So how are these guys related to each other? Well, if it were 5 cycles in a second, it would take 1/5 of a second to complete one cycle. So these guys are inverses of each other. The period and the frequency are inverses. If you know one, you know the other one. And about the only other thing the book does in this section is to just do some calculations of, k delta x equals ma. I'm just going to use a magnitude equation for this one, but they're saying what if, you know the amplitude is a, and you're at half of that? Well, then k, if you're in here somewhere, the mass is half the amplitude, for instance. Delta x is a over 2, could be on this side or this side for mine because I'm not worried about direction right now, equals mass times acceleration. What would be the acceleration of the object? And you would just solve a equals acceleration is k amplitude over 2 times the mass. And that's not something you have to memorize or anything like that. They're just showing how you can plug in delta x is a over 2 and find what the acceleration. So you can see as the amplitude as you're farther out, closer to the amplitude, the force gets bigger, and so the acceleration gets bigger. And then we'll talk in the next section about kind of how we can use energy to talk about the velocity.